So, we got the tangent line. Did everybody do the tangent line?
Yeah.
What is it, Haley?
Give me a second.
So you didn't do it?
Oh my heavens.
Y minus 1 equals x.
Hey, it is y minus 1 equals x e to the x.
Oh, that was as easy as that.
It's not x e to the x.
Just x.
Ooh, it's just
It's not a
x.
tangent line. It can't be a tangent line there.
Yeah, e to the x is the slope, but we want the slope specifically at 0.
Oh, right.
You know what I'm saying? So y prime is e to the x, but we want to know what y prime just at 0 is, and that's 1. So the slope of our line is 1, and then x minus 0. But really, for our purposes, we want to rewrite this as x plus 1. Also, for my purposes, let me cross out this dumb y and put f of x. So we have f of x and we have y, okay? And the purpose of y is that it looks like f of x around the point where we created it, which was x equals 0. True? Okay? So let's go ahead and let's just graph this and see what it looks like. This is going to be fun.
Whoa.
Well, what?
We're from a tablet to the computer.
You could work for Acer, man. X plus 1. So look, you could, if we zoom in, just basically we did this last year, you can see the tangent line and e to the x look the same around that point, right? But the further we get away from 0, where we create the tangent line, the further away that the two graphs become, okay? So what would be nice is, since e to the x is not a line, it's actually a curve, it'd be nice if instead of finding a tangent line, we could find like a tangent curve, or they don't call it that, but something along those lines, okay? So instead of finding a linear equation, maybe we could find a quadratic equation that looked like e to the x around x equals 0, because then it'll kind of bend with it a little bit, okay? So to think about that and to do that, let's think about what a tangent line really is doing, okay? What we did was I gave you this function, f of x, and I told you it's e to the x. And I said I want a new function, which I'm calling y, and I want two things to be true. To find the tangent line, this is what we do all the time. We want f at the point we find it to be the same on both. So I wanted f of 0 to be the same as y of 0, which means they go through the same point, basically. They both have to be 1, right? And I wanted the slopes to be the same there, which means I needed y prime of 0, or f prime of 0, to equal y prime of 0, true? And then from that, I just built the equation that had the same slope and the same point, and that's what gave us that similarity between them, okay? Because it went through the same point and had the same direction, so they had to look the same around there. To go further, to extend this, I could find a new equation that doesn't just match it at the y value and the y prime value. I could get it to match at the second derivative value. Does that make sense? Were you with me here? Okay. So what's the second derivative of e to the x? E to the x. I'm going to call that f double prime of x is e to the x. And just like we just said for the tangent line, when you told me it was e to the x times x, and we said, well, that's not right. We had to plug 0 into the slope, right? We don't want to match this at every single second derivative. We only want to match it at 0. So what's f double prime at 0? Whoa there. Craziness. F double prime at 0 is 1. And we already knew that f prime at 0 is 1, and f at 0 is 1. So this is pretty convenient because they're all just 1. That's not typical of all functions, okay? But e to the x has this property. So I need a new equation, which I'm going to call y again, okay? But it's going to have, actually let's call it p of x for polynomial, because we're creating a polynomial, okay? It's going to have the second derivative equal to 1 at 0, all right? Now, since I don't care about the third derivative or the fourth derivative, what's the easiest way to guarantee the second derivative is going to equal 1? What could I say the second derivative has to equal everywhere? I can just let it equal 1. That makes sense? Let's just let the second derivative just be 1. And then it will match. It'll be 1 and 0. Okay? That's the simplest way to do this. So I'm going to create a p, but I'm going to say that I know that p double prime at 0 has to be 1, right? But I'm just going to say p double prime equals 1 everywhere. You with me on this? And now p double prime of 0 will be 1. So it matches the second derivative. But from here, the reason why I'm starting with double prime is because That's like I need that just to be 1 at 0. I can now work backwards. If p double prime is 1, what's p prime got to be? X plus c, true? It would be x, but there could be a plus c there. And our only condition on the first derivative is what do we know it has to equal? 1 when x is 0. So what's c? 0, -1, or 1? It's got to be 1. C has to be 1.
Oh, yeah.
When you plug in 0, you got to get back 1. All right, and then, so look, all I've done is I matched the second derivative to be 1, because that's what the second derivative of our f of x is. I made the first derivative 1 at 0, and now I'm going to make sure that p of x, which we can get by integrating, goes through the right point. When you integrate that, you get 1/2 x squared plus x plus c. But what's c got to be? C has to be 1. Sound good? Now let's see, let's just take a gander at what happens when so let me go back for a second. Do you notice that our tangent line is right there? The tangent line's at the end of that. All we did was really add a new piece to it, which is kind of weird. Okay? Like that didn't necessarily have to happen, but it did. So let's see what happens when I graph. No, how would I want the x down there? That doesn't make any sense, does it? 1/2. I'm having issues. X squared plus x plus 1. There we go. Now look, you can't even tell them apart. So man, like that's the same graph, but you can't even tell them apart. You know what? Maybe we should have them both graphed, just for fun. So if we take this one away, boom, you can see how different the red and green ones are out at the ends there. But if I graph the blue one and the red one, you can't really tell them apart at all in that window. Which means the blue curve does a better job at approximating e to the x than the green line did. Make sense? And if we zoom out a little bit, you can see the same thing still happens. As we zoom out, it still breaks away from it, but around 0, it looks very, very much like it. Okay? Now, this was like mathematician's idea back in like the 1700s. I don't know when, a long time ago. It doesn't really matter. Okay? And they're like, well, if it worked when we matched the second derivative and it looked a little better, guess what they said? Guess what we should do? Let's match it to the third derivative. Go ahead and do that one.
Right.
We're going to pause now, unpause this. So, to denote these, since we just found p of x in the last one here, and with second degree, I'm going to call that p sub 2. Does that sound good? Which means if we find a third degree polynomial that mimics e to the x, I'm going to call that p sub 3. Now, you would not normally find all of these at one time. The question would be, find the fourth degree polynomial that looks like this function, and you would just find that one. Does that make sense? We're building it as we go along here, just because we're doing it for the first time. But this is not how you're going to do this every single time. But what's the third degree polynomial? Alex, what do you got?
1/6 x to the third.
It's 1/6 x cubed.
Plus what we had for p2.
Plus 1/2 x squared plus x plus 1. Okay? And you can see exact same thing happened. We've got our second degree polynomial there, right here, boom. And all we did was add an extra piece. Really, okay? But let's go back to our graph again. Let me graph this one. Oh, man. 1/6. Get out of there. That should be automatic. X to the third, right? There we go. Plus 1/2 x squared. I can make this easier on myself. Plus x plus 1. Okay. Now, why is that? What's wrong with it? Plus 1. Boom. Okay. So you can see that's this. Let me change the color of this thing so we can see it a little bit better. I don't really know. Orange. Let me do this too. Projector mode. Okay. So you can see the red curve is what we're trying to imitate. All right. The blue curve and the orange curve, and they all converge at 0, 1. Okay. They all go through that same point. But the orange curve holds on a little bit longer than the blue curve does and then breaks away from it. Okay? Now, technically, the orange curve and the red curve aren't the same anywhere except for at 0, 1. Everywhere else, they're just really close to each other until it starts to break away. Does that make sense? Okay, I know it looks like they're the same exact thing in there because like I'm around zoomed in. But if I zoomed in far enough, you would see that they're actually different. Okay, but they're real close together. And it turns out the further we take this out, the better this polynomial becomes. Okay? So we could continue going out, like, let's just do one more for fun. Let's go ahead, we're already on the third. Let's find the sixth degree. That's too much, fifth. Let's find the fifth degree polynomial.
Why not just fourth? Because that was the next
Okay, no, let's find fifth, because then you gotta go one more. Let's find the fifth degree polynomial.
Oh, heavens.
Oh, heavens.
Can you hear me?
Dude, without computers, why is math so important?
Need to calculate the sun or something.
What do you mean? How do you think the computers got developed? Just out of nowhere, someone's like, boom, computer.
Like the 1600s.
Yeah, what did they use math for? Navigation?
They just had to say
There was still science and things going on. There's still chemistry and engineering. Like, they still had to build bridges and do things. Like,
right.
they were still building machines. Someone had to build the first freaking computer. Like, all right, anyway, look. P to the sixth. Oh, we did to the fifth, right? Did you guys get this coefficient? 1 over 120. Oh. X to the fifth. Sorry. It's x over, or 1 over 120 x to the fifth, right? Plus 1 over 24 x to the fourth, plus 1 over 6 x cubed, plus 1/2 x squared, plus x plus 1. All right? And we're going to give this thing a name. We're going to graph it and check it out. But real quick, just so we know, ready for this? This is called, let me change the font. I'll show it in a second. This is called the fifth degree. I know. Come on, it's adorable. What's a good font? 26? 26. The fifth degree Taylor, or it's also called the Macluarin. I think I'm spelling that right. Polynomial. We'll talk about Taylor versus Maclaurin later on. Okay, but these are both the same. All right. Fifth degree Taylor polynomial of e to the x, which is the function that we're mimicking here, which I'm going to write like that for right now since my computer's not cooperating. Okay. And we specifically found it, just like we found tangent lines, at x equals 0. Okay. So that means we could find a fifth degree Taylor polynomial for e to the x at any other x value, and it would be different. It would be a different polynomial. Okay? So, for instance, if we wanted to know what e to the 10th was for some reason, using a polynomial centered at 0 doesn't make a lot of sense. Okay? You would center it probably, well, if you want to know what e to the 10.2 was or something, you'd center it e to the 10, because that's probably a number you could figure out. Okay? And then use that. Okay, so we could change the center on these things. We'll talk about that later on. And actually, let me just tell you the difference between these two. All a Maclaurin polynomial is a Taylor polynomial that's specifically centered at 0. Okay? So I could call this the fifth degree Maclaurin polynomial of e to the x. And then I don't have to tell you it's centered at 0 because it's automatically centered at 0. That's what a Maclaurin is. Okay? So you know how all squares are rectangles? Remember? All Maclaurin polynomials are Taylor polynomials. Okay? But not all Taylor polynomials are Maclaurin polynomials. Cool? It has to be centered at 0 to be a Maclaurin. Okay? All right. Well, let's graph it. Boom. I got a good plan. Check this out. I'm going to call this, whoa there, chief, f of x. And then over here, I'm so smart. I'm going to do 1 over 120, x to the fifth, plus 1 over 24, x to the fourth, plus f of x.
Is that going to work?
Yep. Boom. Now I'm going to change the color so we can tell the difference. What do you like? Green?
Purple.
Black. That'll be better. That's a good call. All right, done. Let's close this. Boom. Oh, my. Okay. So you can't even see. You can see a little bit down the bottom down here. You can't even see that red graph anymore compared to that black graph on the window. Okay? But if you zoom out, now remember, this is still a fifth degree polynomial, so the left side's got to go down and the right side's got to go up because it's a fifth degree polynomial. And you see it happening there, it breaks away. Okay? But it is true that if I keep taking this out further and further and further, I can get a polynomial that will mimic e to the x as far out as I want. But it will also always be true. No matter how far I take out the degree, the further I get from 0, the worse it is at approximating it. That make sense? Okay? So the center matters in terms of like the x value you're trying to approximate, and what the degree you take it out to matters. They both affect the accuracy of your approximation. Okay? But you're feeling good? So then mathematicians, which are crazy old people, they said, look, if this is working out, why don't we just come up with, so for instance, right now, if I say, let's find a 10th degree polynomial, I don't want to go through all this stupid work to find a 10th degree polynomial. I'd like to just have a shortcut. So they say, let's go ahead and find a pattern for this specific function that'll tell me what each term has to look like. Okay? So let's take a look at this. If I want P sub n of x, where n could be any number whatsoever, what will the exponent of my first term be? It'll be n. Excellent, n, friend. N is right. Okay? So it's going to be x to the n, but it's going to have a coefficient on it, just like all the other ones do. Anybody want? Now, we built this. We saw what we did to get all these exponents. To get that 5th degree up here, this 120 came from multiplying what numbers?
4.
Well, 24 by 5, right? Which is a factorial. It was 1 times 2 times 3 times 4 times 5, right? That's a factorial. That's with the exclamation point. Yep. Okay. So remember you learned factorials. You're like, why do we ever need these? All factorials are shorthand ways to write things, and that was the whole point of this. We want to write this in a shorthand manner. So this is going to be 1 over n factorial x to the n. That makes sense. What will my next term be?
That's weird.
1 over n minus 1 factorial x to the n minus 1. Oh, I forgot the factorial. And that will continue. So look, I'm going to do dot, 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 all the way down to the x plus 1 are still going to be there. That make sense? We're good? All right. You look good. Okay. So, this isn't, I know, this isn't really, although that's a great pattern to find. So now if I actually define the 10th degree polynomial, you could write out the 10th degree polynomial. I'm not going to make you do that. It's nuts, okay? But we could do it. All right? Again, computers do a lot of this stuff, and calculators do a lot of this stuff, but we don't do this all by hand. Okay? However, it's really not easy to write still. So because we're adding each term, we're going to use our good friend sigma to write this as a big summation. Okay? So we are going to say that P sub n is really just the summation of all these terms.
I don't remember summation.
Okay? Summation just means add up all these terms. Well, I'll talk about the format here in a second, okay? But each term has to look like, now, normally I use n in my summations, but because I'm calling this P sub n, I have to use a new variable, okay? So, well, I don't use Q. They use I sometimes, or K. I'm going to use K. I like K. Okay? You can use Q if you want to, okay? But I'm going to use K, okay? But every single one of these terms has to look like x to the k divided by k factorial. Does that make sense? How high do I want k to go if I want the nth degree polynomial? High as a kite. All the way to n. Very good. All the way to n. And what should k start at? So I get all the way to the beginning here. 0. And you write that. So all this notation means is we're going to plug 0 into that formula for k. Okay, so check this out. If I plug 0 in there for k, I get x to the 0 over 0 factorial. Now 0 factorial is a weird beast. What do you want it to equal?
0.
It looks like maybe 0. It equals 1. 0 factorial equals 1 by straight up definition. People are like, it fits our pattern, let's just let it be 1. Okay? So 0 factorial is 1. All right? So when I plug 0 into that thing, I get just 1. Plus, we're uncovering the mysteries of the universe here, man.
This actually makes sense, Danny. Come on.
When I plug in 1, we get x over 1 factorial, which is just x. When I plug in 2, plus, we get x squared over 2 factorial, which is just 2. When I plug in 3, I get x cubed over 3 factorial, which is 6, but I write 3 factorial. That make sense? So all this does is list out the terms in a very, very shorthand manner. Does that make sense?
Yeah.
Boom. We're feeling good.
Wait, why is it just 2 for that one and then 3 for 4?
What do you mean just 2 for what one?
For x squared over 2, I did it.
Oh, because what's 2 factorial? You're right, it should be. But 2 factorial is just 2 times 1. It's just 2. Because it's multiplied by every number less than it. So 3 factorial means 3 times 2 times 1. Okay, 8 factorial is 8 times 7 times 6 times 5. Cool. Factorials grow very large. Factorials grow faster than exponential equations. Okay, yeah, they get real big real fast. Cool. Anyway, you put like dot, dot, dot here all the way out to the last term, which would be x to the n over n factorial. Okay? And that right there is called the nth degree Maclaurin polynomial for e to the x. Okay? What makes something a series, what turns it into a series, is if we take our summation. Since this gets better and better and better the further out we go, guess where we want to take it? To infinity. Okay? And that's what the series is. So the Taylor series for e to the x is the summation. And I use n's in here instead of the k I used before, okay? And that's just usually the notation you see in books. But you start at 0 and you go to infinity of that pattern. Okay? And since that thing is going to look like e to the x everywhere, the further out we go, the better it looks. So if you go out to infinity, right, which is really a limit idea, if you keep doing it forever, never, 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 this summation, which is just a polynomial, will look like e to the x. And that's the series representation of e to the x.
That's how a calculator does it.
Okay? So calculators have what's called like proprietary programming. So like Texas Instrument might do something along these lines, but they probably have something that works very quickly, faster than this. Okay?
Only works for e to the x.
Yeah, this series right here is just for e to the x because we built it from the derivatives of e to the x. Easy enough? So you know how we know rules like derivatives for, I don't know, e to the x, sine, cosine, tangent. We just know those rules. We're going to learn rules for series. You're just going to know them. So this is something you're going to memorize. Okay? I hope it makes sense where it came from, but you're just going to know it. Cool. Now, we're not going to do every single function ever. We're only going to do 5 polynomials you're going to memorize. E to the x, you're going to do sine and cosine tonight for homework. Okay? You're going to try to find the pattern. We're going to do 1 over 1 minus x. And what's the other one? Oh, we're going to do ln of x. Okay? Or ln of x minus 1. But we'll get to that. We'll get to that. Does this, we feeling okay? So we're going to do this today. We're going to find a couple series and look at them. But really what we're going to start with after this, we're not going to get super heavy into like Taylor series right away. We need to take a step back and just look at series in general and how they operate. Because does it make sense that if you add up an infinite chain of things, that it might add up to infinity? With me on this? Okay. That's called diverging. So if it adds up to infinity, it doesn't really do us any good. We want it to happen that it adds up and equals what the function is. So it turns out some of these polynomials or series we're going to create, sometimes they converge to the function we want, which means they equal the function, and sometimes they do not. So we're going to take a step back and learn how do we work with these things and see when they're going to converge and when they're going to diverge, just like we do with improper integrals. Okay? But your homework tonight is to find, we'll just go ahead all the way down to like p sub 6. Okay? So I want you to find p sub 6 for cosine of x. Okay? Centered at 0. So another way to say that is find the Maclaurin polynomial for cosine, the 6th degree Maclaurin polynomial. Okay? Same thing. And I also want you to find, let me type it out, because this is how you're going to see it on like a test or the AP exam. Find the, let's get crazy, 36. Oh my God. Find the 7th degree Maclaurin polynomial. Whoa, this is bad. I'm having trouble here. Polynomial for sine of x. All right, and then after you're done that, find the Maclaurin series for cosine of x and sine of x, which just means find the polynomials, figure out what the pattern is, and try to write it in a shorthand form. Sound good? All right. Good work today, Mr. Smith. Thank you, Mr. Smith. All right.